AM, FM, PSK, QAM. You have probably heard these terms before, but they all describe different ways of doing exactly the same thing, placing information onto a carrier wave. So, how can one simple idea produce so many different communication technologies? Let's explore the world of modulation. In the previous lesson, we learned why modulation is necessary. Baseband signals cannot be transmitted efficiently over long distances, so communication systems shift the information onto a high-frequency carrier before transmission. However, knowing that modulation is required immediately raises another question. If the goal is simply to move information onto a carrier, why are there so many different modulation techniques? Why do AM radio, FM radio, Wi-Fi, Bluetooth, and 5G all use different methods? The answer is that each communication system has different design goals. Some prioritize simplicity, others maximize data rate, while others focus on noise immunity or bandwidth efficiency. Modulation techniques are designed to optimize these trade-offs. Modulation is the process of varying one or more properties of a high-frequency carrier wave according to the information contained in the baseband signal. There are three fundamental properties of a sinusoidal carrier that can be modified. Amplitude, producing amplitude modulation, A, math. Frequency, producing frequency modulation, FM. Phase, producing phase modulation, PM. Modern digital communication extends these same ideas by changing the carrier according to digital symbols instead of continuous analog signals. Techniques such as PSK and QAM represent digital information by changing the carrier's phase, amplitude, or both. Although the implementations differ, every modulation technique shares the same objective: efficiently transporting information through a communication channel. Intuitively, imagine driving a car to communicate with another driver. You could vary your speed, change your lane position, or flash your headlights. Each method conveys information differently, yet the purpose remains the same: sending a message. Modulation works in a similar way by choosing different carrier properties to represent information. Physically, consider an RF carrier generated by a transmitter. In AM, the carrier's amplitude follows the information signal. In FM, the carrier frequency changes continuously with the information. In digital systems like QPSK or QAM, the transmitter changes the carrier in carefully controlled discrete steps that represent binary data. Mathematically, modulation changes specific parameters of a sinusoidal waveform while keeping the underlying carrier frequency available for efficient propagation. The receiver later detects these variations and reconstructs the original information through demodulation. Different communication systems choose different modulation techniques depending on their requirements. AM radio favors simplicity and long-distance broadcasting. FM radio provides better audio quality and greater resistance to noise. Cellular networks, Wi-Fi, LTE, and 5G rely on advanced digital modulation methods such as QPSK and QAM to achieve high data rates and efficient spectrum usage. RF engineers must carefully select modulation schemes based on bandwidth availability, channel conditions, power efficiency, hardware complexity, and desired communication reliability. There is no universally best modulation method. Each involves engineering trade-offs. At the system level, modulation determines how efficiently information uses the available spectrum and how well the communication link performs under real-world conditions. Modulation is the bridge between information and electromagnetic waves. Without it, modern wireless communication, including mobile phones, satellite systems, Wi-Fi, GPS, and Bluetooth, would not exist. A common misconception is that one modulation technique is always superior to another. In reality, each technique is designed for specific operating conditions. Simpler methods may offer greater robustness, while more advanced methods provide higher data rates at the cost of increased complexity and stricter signal quality requirements. Now that we have an overview of modulation, we are ready to study individual techniques in detail. In the next lesson, we will begin with amplitude modulation .A and discover how changing the carrier's amplitude allows information to be transmitted over long distances. In this lesson, we learned that modulation is the process of placing information onto a high-frequency carrier by changing its amplitude, frequency, or phase. We also explored the major categories of modulation and saw why different communication systems choose different techniques based on their performance requirements. In the next lesson, we will study amplitude modulation AM and learn how one of the earliest modulation techniques laid the foundation for modern wireless communication. If you found this useful, like the video, subscribe, and follow for the next lesson.